Okay, for our final piece of lesson 17, we're just going to interpret concavity just a little bit more, or the second derivative just a little bit more. I mean, what does it really mean? What are we measuring when we look at a second derivative? Okay. So we kind of just talked about the fact that concavity, or second derivative, is the rate of change, because it's a derivative. What is it the derivative of? Of the derivative, okay? So of f prime of x, which really means of the slope of f of x. Haven't we interchanged the idea that slope of the tangent can be considered the slope of the function? Okay. So the second derivative is the rate of change of the slope of the function. So let's think of it this way. If f double prime of x is positive, that means the slope of f is getting larger. So just like we talked about with acceleration and velocity to tell if something is speeding up or slowing down, when we say it's getting larger, it matters if it's the thing you're talking about is positive or negative. So for example, if f is going up, so it's increasing, right? And it's getting larger, then it's getting steeper in this scenario where the second derivative is positive. But if f is going down and its slope is getting larger, that means it's getting less steep. So it is a little bit more of a problem solver, of a deeper thought. You can't just look at it and say, oh, it's getting steeper or it's getting less steep, because you have to look at both the second derivative and the first derivative. So let's look at an example here. Okay. The following figure shows a population growth for honeybees raised in I guess that's a place where you raise honeybees. How does the rate of population growth change over time? When is the rate the highest? Over what intervals is P concave up or concave down? So you can figure that part out pretty quick by just looking at this. So this is a graph of P, number of bees in thousands, over this time. And you can see here, we have where it would be concave up. Okay. And somewhere around here, it changes concavity. And that's where it's concave down. We could write that down in terms of intervals. So when it's concave up, that means that the rate of change is increasing. The derivative is increasing. The derivative is the change, the rate of change in the population over time. Okay. And so where it's concave down, that rate of change is decreasing. So two just very simple statements of what concave up and concave down mean. So let's talk about what the rate of change itself is. Since this is n, right, over t, the rate of change of the population, let me write that first. Okay. The rate of change, which is dn dt, okay, is the change in population of bees in what, bees, number of bees per week, since time is in weeks. So at any given moment, like here, that dNdt would be how many, what the change in population, the change in the number of bees per week would be after 6 weeks. Here, this derivative would be the rate of change in how many bees per week, right? So that's what that means. Notice that this population graph is always positive. So what would you expect of dn dt? It's always going to be positive since p is increasing. Okay. This function, I think I just said positive, I meant increasing. It's always going up, right? It's going up at different rates. It's always going up. So its derivative is always going to be positive. It's always going to be positive because this is always going up. So the question is, when is this rate? When is this the highest? So when this graph is concave up, this rate is increasing. I said increasing, didn't I? Is. So this rate, this derivative, this rate is increasing, getting bigger and bigger. It's positive, so it's becoming more, larger and larger positive number until right about here. And then what happens? It starts to decrease. Is it still positive? Yes, because this function is still increasing, but it is now getting smaller. So maybe it's 5, 6, 7, 20, I don't know. But then it goes back down to 18, 12, 10, etc. Okay. So how does the rate of population growth change over time? Well, it's positive, and it increases until right about, I don't know, 11 weeks or so. And then it starts to decrease. Okay. So we could say it's always positive and its max rate occurs at approximately 11 weeks. So we've kind of answered all the things. We talked about the fact that it's always positive. We talked about where its maximum is, and we identified it by color where the intervals were positive and negative. So it definitely takes a little bit more interpretation and kind of understanding that concavity is telling you about what's happening with the derivative when the derivative is increasing and decreasing. So there is a similar problem right below here. And I want you to pause the video, read the problem, and give it a try. Okay, so we're looking at a sales over a certain time, 3-year span, and the sales themselves decreased for the first 2 years and then finally started to pick back up. So we know that the derivative itself, the rate of change of sales, is negative until it's positive. Okay, so S prime, the derivative, is less than 0, is negative for the first 2 years. But look at concavity. This graph is concave down till about here. Might be a little, it's hard to tell exactly where that inflection point is, right? But then it becomes concave up. So what does that mean? When it's concave down, the second derivative is 0, which means that the first derivative is decreasing. So in this period of time where the derivative is already negative, it's decreasing, so it's becoming more negative. Sales are down and they're going down faster. They're getting more down. Then at this point, the second derivative is positive, which means that the first derivative is increasing. The first derivative is still negative, but it's becoming less negative. So it's, if it was negative 10 here, now it's negative 8, negative 6, negative 1, until it finally turns around and becomes positive. So it's asking the point when the sales are decreasing at their greatest rate. The sales are decreasing and becoming more negative until that point of inflection where then they start to become less negative. So it's right there, and I think I called it at t equals 1. It might be 1.1, or I'm not sure, but right around there is the point where the derivative, which is a rate, is the lowest. Okay, the sales are decreasing at their greatest rate. Okay, and then last but not least, I just wanted to identify a second derivative test, which we actually don't have using much because the first derivative test is much more helpful. But go ahead and read that what it's telling us is if we have a first derivative that's 0 and the second derivative is positive. So if it's concave up and there's a point with a horizontal tangent line, what are we going to have there? A local min. Whereas if the first derivative is still 0 and the second derivative is negative, so it's concave down, and there's a point with a horizontal tangent line, pretend that was actually horizontal, then that's going to be a local max. The reason we don't use this is that this test is inconclusive. If you find the second derivative is 0 at that point, it doesn't tell you anything. It doesn't mean it's a max, it doesn't mean it's a min, it doesn't mean it's neither. It's just, you can't say anything. It's kind of like 0 over 0 in a limit. And that's not very helpful. And if we wanted to find maxes and mins, we just use the first derivative test. So the second derivative test shows up and they point it out, but we don't actually use it much. So there it is. All right. So I do have 2 more problems here. And these are just kind of using all of the ideas in this function and this lesson, sorry. And the first one I think is really important to take a minute to look at, because what's happening here is we're getting the same information we've been doing by taking derivatives and making sign graphs, but they're giving it to us in a graph, in a picture. So this is the graph of the derivative. This is the graph of the derivative of f. And then the question is, on what intervals is f, not f prime, f, increasing and decreasing? And where does it have a local maximum and a local minimum? Okay, let's start there, then we'll do concavity. So remember, we know that a function is increasing if its derivative is greater than 0 and decreasing or decreasing when the derivative is less than 0. So if you're looking at the graph of the derivative, you're trying to figure out, when is this graph bigger than 0? And when is this graph less than 0? So it has nothing to do with the maxes and the mins of the derivative. It has everything to do with when the derivative is positive and when the derivative is negative. If that messes with your brain, which it often does, make a sign chart, right? So when is this derivative equal to 0? At these 3 places. And what's happening on the left side of 1? The derivative is negative because it's below the x-axis. What's happening between 1 and 6? The derivative is positive because it's above the x-axis. Between 6 and 8, it's below the x-axis and then it's back above. So that means the original function is increasing and decreasing in this manner. Really throws a lot of people off, okay, because of the fact that you look at this and you want to say it's 0 here and 0 here and 0 here, but that would be when the derivative of this graph, which would be the second derivative, right? But we want to know when the original function is increasing and decreasing. Okay, so we could answer those questions. I don't think I'm going to write out all the answers, but you can say it's increasing on 1 to 6 and 8 to infinity, and then decreasing on negative infinity to 1 and 6 to 8. Also looks like it's going to have a local max. Let's write that bit out. Local max at x equals 6 and a local min at x equals 1 and x equals 8. I can't plug it in to find out what the actual maxes and mins would be. Okay, and then the second part of this question asks us, what about concave up and concave down? So again, the idea is, okay, we need to create a sign chart for F double prime. And that one we are going to need to know, when is F double prime 0? Well, if this is F prime, we're looking at where does it have horizontal tangents. So that would be at 2, 3, 5, and 7. And then we need to fill in whether they're positive and negative in each of these places, which would just be, again, F double prime is just the derivative of this graph. So we're looking at increase, positive, decrease, negative, increase, positive, etc. So it looks like it would fill in as plus because it's increasing, then it's decreasing, and it looks like it really is just alternating, right? So again, I'm not going to write out all of these intervals. We could write down concave up, concave down at the correct intervals, and all of my inflection points appear to be happening at x equals 2, 3, 5, and 7, since it changes concavity at each one of those points. So this problem is really more of a intuitive understanding, not just going through the motions of taking a derivative and so forth, but actually really understanding what you're looking at graphically speaking and being able to interpret how those graphs are related to each other, which is a critical aspect of what this lesson is talking about. All right, last but not least, there is a problem here that asks you to find the relative extrema, find the concavity, points of inflection, and use that information to try to sketch the curve itself, which I don't know that you're going to have quite enough. So let's skip that part of it. We're going to put more information together, but just go through and take the derivatives, find relative extrema, concavity, etc. So I'm going to have you pause the video and go through the motions of doing that. When you unpause, I will have the work set up, but I'm not really going to talk through it much. I'm just going to let you check your work. Okay, I've worked through just the first part here, where I've taken the first derivative, simplified it, set it equal to 0, and figured out where it's undefined, and then made my sign chart. So you will notice that with these fractional exponents, these derivatives get kind of gross, but they're essential that you're able to do this. So I did the same thing where I factored out a coefficient and the lowest power of each of these terms. And then I had something pretty easy to deal with left inside. I factored a 3 out of here and canceled it. So that's how I ended up with this. I'm going to want that as simplified as possible before I go on to take a second derivative. So again, pause the video here, double check your work on the first derivative. And then once you're confident in that, go ahead and move forward onto the second derivative. Okay, this one is a doozer for sure. But I gotta tell you, if it doesn't convince you that you can't just try to multiply everything out, then nothing else will. You will have something along, not necessarily this complicated, but you will have to take derivatives that are not just straightforward polynomials and easy to multiply out things. You have to be able to have the algebra to simplify complicated expressions. So I know it's a lot. I did my derivative. When I do my derivative here, where did my first derivative go? Here it is. I have a quotient rule, but then when I do the derivative of the denominator, it has a product rule and a chain rule as well. So in my first line, I've just done low d high minus high d low, all over low low. And what I've done next is I've looked at this, everything that's kind of a group, and this multiplied together. So you can distribute this first. So there's three terms, 1, 2, 3, and each one of these two has this in it, right? It's distributed. And I've factored out this GCF. And then here are the three things left over. That's the big step from here to here. Because now both of these just kick down to the denominator. So the 2/3 and the 2/3 will add, 1/3 and the 4/3 will add, the 3 just comes down. Multiplied everything out inside there, and everything cancels, right? Except down to a -8 after all of that. So if you can get to here, you've won the battle. Let me just make it a little smaller so you can see the whole thing. So then the final pieces are just figuring out that this doesn't exist at these 2 points, throwing those on a sign chart, doing my pluses and minuses, and seeing that it only changes concavity in one place. Oh. Uh-oh. Sorry about that. All right, well, I just realized that my screen sharing had paused while I was walking through that. So I'll try one more time. Not sure where it stopped pausing, so you can just stop watching the video if you saw enough of it. But this was my low D high minus high D low. Then from 1, 2, 3 terms, just distribute this. So this 4 minus x is part of this and this. So I have 1, 2, 3 terms. I'm factoring out my GCF, leaving me with 1, 2, 3 pieces left inside. These all kick down to the denominator because they're negative exponents. So the 2/3 adds to the 2/3, the 1/3 adds to the 4/3. And then if I multiply out what's left, everything cancels to just -8. And then I can finish out my problem as I just described. Okay, so go ahead and pause and take a look at this for as long as you need to try to get your algebra to line up. And then go ahead and start the lesson homework.